Okay, got it. Thank you so much, Craig. Thank you everybody for joining me on this afternoon talk. My name is Tshiamo Moleele. So my talk is going to be centered on carbon capture and sequestration technology. So this is more just of an information sharing so that people can learn about what this technology is about. So these are basically a few things that I'm going to be going through in the course of today's talk. So what is CCS? So CCS is CCS is essentially capturing carbon dioxide and preventing it from being released into the atmosphere. And this technology was first suggested in 1977 as an it used existing technology in new ways. So carbon capture has been used since the 1920s as well for separating carbon dioxide, sometimes from natural gas reserves from sealable methane gas. So sometimes you hear CCS, CCUS. So basically it's carbon capture utilization. They're used interchangeably. This is because CCS in itself is it's a relatively expensive process which yields a product of intrinsic low value. So the U of it is where you can get a lot of value out of it. So in 2015, the International Energy Agency considered CCS to be one technology which can contribute to the objective of decreasing greenhouse gases emission between 50% to 80% by 2020. And this kind of reduction is needed in the prevention of the rise of the global average temperature from exceeding the 2 degrees Celsius threshold by the year 2100. So this image just shows you the processes involved in storing carbon dioxide. So the process of capturing anthropogenic carbon dioxide from a large point source, and then you transport it to a suitable site, and then you permanently lock it away. As I've said before, the purpose of it is to reduce our carbon dioxide footprint from burning of fossil fuels with the aim of mitigating the global warming. So there are three processes involved, namely then when you produce carbon dioxide, when you capture it, transporting it, and injecting. So injecting is the same thing as storing. And these processes, they contain a lot of parameters, processes, and phenomena, which must be measured, recorded, and monitored to ensure that the injected carbon dioxide remains confined for thousands of years without seeping back into the surface. So for the duration of this course, I'm just only going to be explaining to you the capture, the transport, and the injection process, because I'm sure everybody knows how carbon dioxide is produced. This is just a slide just to show you how carbon capture and storage works. So when we're talking about capture, carbon dioxide can be captured from a large source meaning a power plant, a natural gas processing facilities, or some industrial processes. And capturing can also happen from the open atmosphere. So when we're talking about burning of fossil fuels in terms of power plants as a capture site, there are three techniques that can be used to remove and capture the carbon dioxide, namely post-combustion, pre-combustion, and oxy-fuel combustion. So in the process of pre-combustion, this is a process where the carbon dioxide is captured before fuel consumption. And you can see the process in this diagram. So what happens is that the carbon dioxide gets separated from the fuel by combining it with air or steam in order to produce hydrogen for combustion. And then a separate carbon dioxide stream could then also be stored. The hydrogen that is produced can be used for electricity production, or it can be used to power cars or heat up homes with near zero emission. This technology is also applied widely in fertilizers, chemicals, gaseous fuel, and production. So this application, along with the separation technologies, I'll show you guys the methods that are used in the next slide. This is basically just the methods and the types of separation technologies that you can find in pre-combustion. You can find absorption by a physical solvent, a chemical solvent, or a porous organic framework. The next kind of capture that is there is post-combustion. This technology involves capturing carbon dioxide during the fuel combustion. So unlike the pre-combustion purposes, this one uses oxygen instead of air for combustion, where the oxygen here is separated from the air prior to combustion. So once the flue gas is enriched with the oxygen, it is then used for combusting the fuel as to produce more concentrated carbon dioxide stream for easier purification after separating from the water vapor. And so the carbon dioxide here can be compressed, transported, and then stored. And this is a table showing you the separation techniques that are found. So this one has a little bit more than the pre-combustion. And then the last technique in terms of capturing CO2, this is when the carbon dioxide gets captured after the fuel is burned. And then this involves extracting carbon dioxide from the flue gas following the combustion of fossil fuels or brine. So the chemical solvent of ammonia or proprietary amides is the principles that are used, and then this is used to capture large quantities of carbon dioxide from a flue gas. And then this there's only one separation technology, which is separating oxygen of the air. These three technologies of capture, they're not the only ones. There are other techniques that involve capturing. These involve physical, chemical, and biological processes. And then the sorption and the membranes are the two major chemical and physical technologies for carbon capture. Whereas when the biological technologies can be used for capturing carbon dioxide from a point or from a non-point sources. And the technologies that are biological, they normally combine the capturing and the sequestration all together. And then the next thing, once now you've captured the carbon dioxide, you need to transport it. And transporting of carbon dioxide is a necessary process of CCS, because once you get the carbon dioxide at a desired purity, but when I mean a desired purity, I mean when carbon dioxide is at supercritical form, it needs to be injected and stored somewhere. And why this it needs to form, the reason why we choose to move, or it's better to move carbon dioxide in its supercritical form, it's because this helps improve the efficiency of it, and it also prevents a two-phase flow of the impurities such as hazardous gases and some of the water also, because they will need to be removed in order to prevent corrosion and to reduce health risks, especially if your storage source is located in a populated area. So the distance between where the carbon dioxide is captured and where it's stored, it varies. And so as a result, there are multiple transporting mechanisms, such as pipelines, road, trucks, and ships. So pipelines it's a likely method to be used to transport large quantities of carbon dioxide. This is because around the world, there's already millions of kilometers of pipelines that exist. And so when you're transporting using trucks and rail, this is only possible for small quantities of carbon dioxide. And then when you look at ship transportation already in the petroleum industry, they use large shipment. They use large ships for shipping liquefied petroleum gas. So there already is an infrastructure there when it comes to large scale of shipping, and that's where you can use it for small quantities or for large quantities. And so now you've captured this carbon dioxide, now you've moved it. So now where are you going to put it? And so there are three main ways that carbon dioxide can be stored. It can be stored in a deep geological storage, it can be mineral storage, or it can be ocean storage. So in the mineral storage, the captured carbon dioxide, they react naturally with occurring iron, calcium, and magnesium minerals. This is what you call mineral carbonation. And this occurs naturally when in the weathering of rocks over time. And these minerals are very abundant and very stable. And as a result, they re-release carbon dioxide into the re-releasing of carbon dioxide into the atmosphere doesn't happen. However, these carbonation reactions happen very slowly under normal conditions, and to speed it up to the quantity that we would be looking for, you would need a tremendous amount of energy to increase the temperature and pressure to ideal levels. So in terms of looking at the big picture of mineral carbonation, it is not the greatest option right now, based on the three. And then the second one, you get deep ocean storage. So when we store carbon dioxide in the deep ocean, what happens is that this will increase our ocean acidification. And this is a problem that we already have, because there's already an excess of carbon dioxide within the atmosphere and the ocean. And so the geological storage in geological formation seems the most promising storage site, and throughout the world, it is largely considered the most promising. So that's why I'm going to delve in. So there are various ways actually that carbon dioxide can be stored geologically. A geological storage is essentially the process whereby the carbon dioxide is injected into and is stored into a suitable deep-seated porous rock structure. And then this rock strata has to be within 800 to 3,000 meters, where temperatures and pressures are above carbon dioxide critical point of 31 degrees Celsius and 7.38 megapascals. So storage can be either on land or under the seabeds. And there are a few sites, if you look at the diagram here, where you can store in geological formation. You can store it in a depleted oil gas reservoir. It can be under a user of carbon dioxide in enhanced oil recovery. It can be in a saline aquifer. It can be in unminerable coal seams. One thing about the state of this carbon dioxide that we be using is that supercritical carbon dioxide behaves like runny liquid. So this makes it so much easier for us to directly inject it into the rock. And the rock that we will be directly injecting into is a sedimentary rock. So, so we'll be looking at sedimentary basins. So a sedimentary basin is essentially a broad-like feature that resulted from a depression of the Earth's crust through the accumulation of the thick sequences of sedimentary rocks, which include shales, sandstones, and coal. And carbon dioxide storage is particularly suitable in these sedimentary rocks because of the pore space that is within the structure. And these pore spaces in the rock, it's a volume whereby there is no mineral matter within that. And then this allows for passage or absorption of fluids. And then we are focusing on the absorption of these fluids. And the best way for the absorption of these fluids is for it to be in a sandstone. So the first one, the deep saline formations, when I say that, I refer to any saline bearing, any saline water bearing. So a saline formation is essentially sealed. It's essentially, the reservoir is a sandstone, and then it has a caprock, and this caprock is normally a shale. And then this is perfect for permanent storage, because the carbon dioxide is going to be injected into the pore spaces of the sandstone, and then the caprock, which will be the shale, will make sure that there's no seepage that happens. And obviously, when you do that, you must also look at the trapping mechanisms that exist within the sandstone itself. And then when we look at coal-baked methane, this is whereby the carbon dioxide is injected into the coal bed to exchange, there will be an exchange of the methane with the carbon dioxide. And then the carbon dioxide will bind to the coal, and then this will ensure permanent storage. And currently, this type of storage is in the research phase. There are currently no projects happening at the moment. And then you get enhanced oil recovery. So this involves injecting the carbon dioxide in order to increase oil production from really mature oil fields. And then the last one is where you find it in depleted oil or gas fields that are no longer that are no longer economical for oil and gas production. And the reason why these are good spaces is because there's already an established trapping and storage characteristic. So I'm going to delve a little bit more into the oil enhanced recovery, because it's one of the popular ones that a lot of countries have been using throughout. So with oil enhanced recovery, what happens is that the carbon dioxide gets injected into a mature oil field that has been used for enhancing oil production. And oil production has been happening for over 40 years. So when I talk about enhanced oil recovery, I refer to a suite of techniques that have been applied to reservoirs with declining oil production to either maintain or improve production. And then most of these fields are considered for enhanced oil recovery have already undergone primary production, in which the natural reserve pressure have brought out the oil into the surface, and they've also undergone secondary production methods whereby you inject water to restore the reservoir pressure. So using carbon dioxide for enhanced oil recovery has been proven to be successful in the rejuvenation of the oil production in many mature oil fields, and this has extended their production lives by decades. And the degree of improvement in the production is really highly dependent on site-specific reservoir characteristics, because no site is the same, and as well as the oil composition that you find there. And it must be noted that not all oil mature fields are amenable for carbon dioxide enhanced oil recovery. This option is particularly quite attractive for people because of its cost injection. Because this cost injection can be partially offset by the sale of the additional oil that you recover. But however, there is a subsequent burning of additional oil recovered through enhanced oil recovery that will offset all, if not much of the reduction of the carbon dioxide emission. So before I continue, I just wanna touch on you get CCS. Some people say CCS, some people say CCUS, some people say CCU. So I just wanna explain the U portion of this whole thing. So when we talk about carbon capture and utilization, what we're talking about this is the process of capturing carbon dioxide to be recycled for further usages. So the CCU offers a response to the global challenge that we have in terms of significantly reducing our greenhouse emissions from major industrial emitters. So how CCU differs from CCS is that CCS does not aim nor result in permanent geological storing of carbon dioxide. What it does is that it aims to convert the captured carbon dioxide into a more valuable substance or product. And then these products can be plastic and concrete, biofuel. And this happens while retaining the carbon neutrality of the production process. So CCUS carries a considerable strategic value as a climate mitigation option, and it can be applied in a number of various ways and across various sectors. And this offers a potential of contribution to the reduction of our emissions directly or indirectly in all parts of our global energy system. And as a result, developing or progressing and the development and the deployment of the CCUS technology in one sector, what that will do is that it will have a significant spillover benefit to the other sectors and application. And this will include technology learning, cost reduction, infrastructure development. And there are really 4 ways in which CCUS can contribute to the transition of the global energy system to a net zero. The first one is that it'll be tackling emissions from existing energy offsets. The second one is that it'll be providing a platform for a low carbon hydrogen production. The third one is that it will be a solution for sectors with hard to abate emissions, like the fossil fuel coal industry. And then lastly, what it will do is that it will remove carbon from the atmosphere. And this is just a map of the world, and then it just shows the location sites of all the carbon dioxide storage sites that are being planned or underway. And currently today, we have about 21 CCUS facilities around the world that have a capacity to capture up to 40 metric tons of carbon dioxide a year. And some of these facilities have been in operation since the 1970s and 1980s. And then the countries currently right now that are leading enhanced oil recovery in commercial projects are the United States, Norway, Canada, China, Australia, Saudi Arabia, and the UAE. And then the first large-scale deep saline aquifer CO2 capture and injection project that was dedicated specifically for carbon dioxide monitoring and storage. This was commissioned at the SACNASP offshore gas field that you find in Norway. And this happened in 1996. And today they have stored more than 20 metric tons of carbon dioxide in saline aquifers. So this is a diagram that I found from the Global CCS Institute. And then it shows you from 2010 till 2020, all the CCS projects that are either operating, under construction, or at an early development, or at an advanced stage. And if you're interested, you can go to the Global CCS Institute website, where you can find a report of the current status of the global status of CCS in 2021. So where is South Africa regarding CCS? So this atlas was released in 2010, and it is essentially an assessment of the storage potential that you find in our country. And then it was done by the Council of Geoscience, and then all the partners involved are there at the bottom. So what this atlas concluded? It concluded that the total storage in South Africa can be found in the Mesozoic basin, which is essentially around the coasts of South Africa. So the Mesozoic basin that you find in the west, in the coast of South Africa, it was formed about 252 million years ago to 66 million years ago. And then the storage potential that is found here, you find it in saline formation that are associated with the sequences of Outeniqua. Outeniqua are the middle, are the dots that you find there in the middle. And then in the Orange Basin, the Orange Basin you find there on the left-hand side, and then as well as the Zulu Basin. The Zulu Basin are those red dots. So what was found in the atlas is that there was a theoretical estimate that storage can be found to be about 150 gigatons. And then since this publication, it stated on the website of the Council of Geoscience that the work that they have done based on the atlas focused on 3 potential storage basins, which are the onshore Zulu Basin, Zululand Basin, the Algoa Basin, and the offshore Durban Basin. And then currently they have a new project that is set to begin, where they're going to be focusing on the potential for site monitoring at the Bangoa natural carbon dioxide gas release that is near Harding in the KwaZulu-Natal. So I believe that having South Africa involved in CCS will definitely benefit our country significantly, as we are a coal-consuming economy, and this technology is much needed because it will allow our country and other developing countries to continue using our domestic energy-based systems, as this technology will assist us to still use fossil fuels whilst transitioning to a net zero. So in summary, I pretty much just went through the processes involved in capturing anthropogenic carbon dioxide, whereby you capture it from a large point source and then you transport it to a suitable site, and then you lock it away permanently. And then the purpose of this technology is to reduce our carbon dioxide footprint from burning of fossil fuels with the aims of mitigating global warming. And then I explained to you that there are various ways at which carbon can be captured. Obviously, when it's captured from a large point source, whether it be a natural gas processing facility or a power plant, and then there are various techniques into capturing. You can capture it post-combustion, pre-combustion, and oxy-combustion. And there are also biological and chemical ways of capturing CO2. And then once all the carbon dioxide is captured, has to be transported, and then it's best to transport supercritical carbon dioxide, and the distance of where the capturing side and the storage side varies. So there are various ways of transporting. You can transport it via pipelines, trucks, railroads or ships. And then there are three main ways to actually store carbon dioxide, and there is ocean storage, mineral storage, deep geological storage. And we found that the geological storage is currently the most promising that, to be done. And then there are 4 ways to do it. You can store it in a deep saline formation. You can store it in a coal bed methane formation. You can store it using enhanced oil recovery. You can also store it at a depleted or oil or gas fields. And so, and then you understood, I explained also that the U in CCUS is there so that carbon dioxide can be recycled for further usages, and that CCUS essentially carries a considerable strategic value as a climate mitigation option. And if you want to find out more in terms of what globally is happening regarding CCUS, the Global CCS Institute is the best place for you to learn in terms of what's happening in the reports, what in depth of what each country is doing, and where they're going and where they've come. And then there you can learn more in terms, because I didn't focus on the financial or the policies related into that. So the Global CCS Institute website is a good place to find out more about that. And then regarding South Africa has found that we can have the ability to store about 150 gigatons, and that it can be stored in saline formation at the Outeniqua, the Orange, and the Zululand Basin. And I conclude by saying that this technology will definitely assist most developing countries that are still using fossil fuels to transition to a net zero economy while still retaining the energy sources that they're currently using. Thank you.
Thank you, Tshiamo. That was very interesting. I found it to be a very good overview of what's going on, and I hadn't realized the complexity of a lot of these projects. But it sounds like things are happening all over the world. Before I open it to questions and comment, I just have one for myself. You didn't mention seismicity. In any injection process, is increased seismicity being looked at in some of these storage formations?
Well, the seismicity gets into play when you get to look at a storage site, because there's a lot of things that have to go before you conclude at a storage site. You have to do site characterization. So seismicity comes into when you characterize the site, because you have to look how large the reservoir is, how much it can take. You have to look at the trappings, and then for you to look at the trapping mechanisms and the faults there, that's where seismicity comes into play.
Yeah, the last thing you need to do is lubricate a major fault, I guess.
Yes, yeah. So seismicity is very important in ensuring that the formation that you have is sound, and that you don't incur any migration throughout time. Because the other thing that I didn't touch into is that once ejection is done, there's a whole new process of monitoring, because then you have to monitor in terms of looking at what's going to happen and how the carbon dioxide is going to behave within the formation that you put it in. Is it going to be forming part of, is it just going to stay there permanently and not interact with the minerals associated with the formation? Or what happens also when the carbon dioxide interacts with the minerals within the formation? And then sometimes you might have a multi-layered formation, so it might migrate and seep above. So what happens in that and in time? So yeah, seismicity is very important, and it helps to alleviate some of the risks that one can find in monitoring. Like right now, yeah, a good project to actually look at is the SACNASP project, because right now they're busy on the monitoring of one of their projects.
Are there any other comments or questions? Please unmute your mic and fire away. I don't see any.
I just want to say it was fascinating. Thank you so much.
Thanks, Nelly.
Well, with that, if there are no more comments or queries, I think you've given us some food for thought. There's all kinds of questions around this, like job creation, mass balance calculations, storing other countries' gigatons, and et cetera, et cetera. So good luck with your thesis. And with that, I'll close the meeting. Thank you very much for talking to us today.
Thank you so much, Craig, and thank you so much, GSSA, for having me on the Lunchtime Talk.
Nalini, any final comments from you?
Just a great weekend.
Nalini, you weren't coming through so clearly there. I think your line is suffering from bandwidth shortage.
Yeah,
But anyway, thank you very much.
It was really interesting.
Yeah.
Thanks, Lisa.
Okay, thank you very much. I'll close the meeting.
Bye.
Ciao.
Ciao, everybody.
Bye.